Hello everyone, and welcome to our first lecture this semester. In this video lecture, I will be covering the first chapter in the course, and that is chapter 22, Electric Charges and Forces. In this chapter, there are two major topics that I'm going to be covering. First is Coulomb's law, and the other one is the electric field. Next chapter, the following chapter, chapter 23, is going to be exclusively on the electric field, where we will be doing more advanced problems. In this one, we will basically introduce the electric field, and we will be doing some problems. So those are the two major topics. Please make it a habit to read the chapter, the entire chapter, and look up the PowerPoint presentation before you come in and view the video the weekly video. The reason for that is because it is almost impossible for me to create video lectures that covers every single thing in each chapter. It would probably take me hours and hours of video time, which is something I cannot do. I cannot look at the screen for hours. It just hurts my eyes, and I'm sure you know that. Unlike being in a face-to-face lecture. So that's very, very difficult for me. So the concentration of the video is going to be on working out problems from the book. One of the reasons I chose this book is because it has excellent collection of problems, whether the examples or some of the problems in the end of each chapter. There's a really nice problems there. So the concentration here is to work out as many problems as possible within, say, an hour or an hour and a half of each video. Keep in mind, you as someone who is majoring in engineering or one of the hard sciences such as physics, you are expected to develop a strong skill in how to solve physics problems. Just like you have hopefully developed a skill in solving math problems, whether it's calculus or differential equations, you also need to develop a skill for solving physics problems. The reason for that is because as an engineer, for example, you will be spending most of your life really just working out engineering problems. And the foundation of engineering is what? Is mathematics, advanced topics in mathematics such as differential equations, which is based on calculus, and physics. So you need to take this matter very seriously. Me as your instructor, as your professor, I realize that, and I am going to be doing a lot of problems. So the reason for that is because I want you to develop that skill. Learning physics and math, as you know, is not. It's like learning the guitar. You know, you have to keep practicing until you master it. You cannot read a book about the guitar and become a great guitarist. It just doesn't work that way. You got to do a lot of practice. Same thing with physics and mathematics. So work out as many problems as you can, and that's how you become good at it, and hopefully when you graduate you become a good engineer. Okay, so anyway, let's jump into the chapter. I thought I'll just give you this introduction, this advice. Probably a lot of you don't hear it from a typical professor or from your parents, but I am telling you that. So I hope you will take that seriously. Okay, so like I said, there are two topics that we're going to be covering. One is Coulomb's law and the electric field. Again, I hope you've read the book, so I'm not going to be talking conceptually about what is Coulomb's law and what is that. So I'm just going to go over them very quickly, and then we'll jump into some of the problems that I have prepared for you. So I'm going to be using OneNote. I'll take the book away for now. I'll come back to it. And so we begin with Coulomb's law. And Coulomb's law basically tells you about the force between two charges. As you know, there are two types of charges, one negative, one positive. The symbol of a charge, by the way, is Q. Whoops, I am at the top of the screen. I'll put it here. Q, and this is how I write the Q. So when you see that little scribble, that's a Q. So we have here a negative charge and a positive charge. And as you know, opposite charges attract each other. and like charges such as positive, they repel each other. Okay, we all learned that back in middle school science and so on. Coulomb's law allows you to measure the force between the two charges, whether that force is attractive or repulsive. Okay, so the law says, well, let me tell you something before that, something that you've studied in the mechanics course, Physics 180. As you know, if I have, let's say, two bodies of mass, this is mass m2, this one is mass m1, and let's say they are separated by distance r, away from the, distance between their centers, there will be a gravitational force between them, and this gravitational force is equal to the product of the two masses divided by their distance squared, up to a constant, we call it g, correct? It's called the universal gravitational constant. As you know, this gravitational force, F, we refer to it as an inverse square law. Why do we call it that? Because it is proportional to 1 over r squared, as you can see here, okay? So it's an inverse square law. And in other words, what that means, it means that the further away the masses from each other, the weaker the force. So the larger they are, the weaker or the smaller the force. Okay. Now nature happens to have the similar structure for the electrostatic force. If I have two charges, say one positive and one negative, and they're separated by a distance r, this is, let's call that Q2. This is Q1, so there will be a electrostatic force between them, that force of attraction between them, the one that will bring them together, and that force is equal to the product of the two charges, Q1 and Q2, divided by the distance between them, between their centers, that is, squared up to a constant, we call it K, where K here we call it the electrostatic constant. Static constant. Okay, and this electrostatic constant K is equal to approximately 9 times 10 to the 9 Newton meter squared over Coulomb squared, where the Coulomb is the unit of the charge, right? Another expression for K is this one, is 1 over 4 pi epsilon naught, where epsilon naught here is a constant. We will learn later about this constant when we cover electromagnetic waves, and it's called the permittivity of free space. You can read about it in the book or on the web if you are curious, and it is a constant. It's equal to 8.85 times 10 to the negative 12, and forgot what the unit is. There it is. It is Coulomb squared. I'm coming from my book, the hard copy here in front of me. Newton meter squared. Okay, so that's called the permittivity of free space. So if you take this number, and if you take this number right here and you plug it into this expression, you will get this number. Okay, I mean to be exact, it's actually not 9, but it's 8.99. But that's really close. I use 9. I never use 8.99. That's good enough. Anyway, so there it is. So this is called the electrostatic constant. Before I forget, let me just talk a little bit about the unit. So a charge, Q, has the unit of Coulomb. The bracket means unit of. And it's big C, the Coulomb here. And the Coulomb, by its own nature, is a very large unit, okay? So we don't really use the Coulomb. We use nanocoulomb, microcoulomb, or even sometimes picocoulomb. Nano means 10 to the negative 9 coulomb, which is a billionth. Micro, 10 to the negative 6 coulomb, which is a millionth. And then the pico, P-I-C-O, is a trillionth, 10 to the negative 12 coulomb, okay? The reason is because the Coulomb, C by itself, is a very large unit. Think of it like, imagine I'm trying to measure your height in miles. I mean, it's possible, it's legal, you know what I mean? But it is just, your unit doesn't fit your height. Your height is much, much smaller than a mile, so what would be more appropriate is a meter or a centimeter or a foot or whatever. right? So the same thing with that. So the charges that we deal with are really tiny, very, very small. Maybe back, when they invented the Coulomb unit, I don't know, maybe the 18th century or 19th century, they were dealing with very, very large apparatuses, and those apparatus were, required a lot of electricity, so they used the Coulomb. But for now, we deal with subatomic particles and so on, or small ions and so on. And so it's more fitting to use the nanocoulomb, the microcoulomb, and the picocoulomb. So almost 99% of the time you'll see those units rather than the coulomb by itself. Anyway, there we go. So let me just give you a simple example and show you how the Coulomb's law applies. And then we'll dig into a more difficult problems. So I'm just going to come up with something from my head. I'll say, for example, I have two charges, and let's assume they are, let's call it charge 1 and charge 2. I'm going to call this charge 2. This is charge 1, Q1 and Q2. Let's make them both positive. How about that? And let's say they're separated by distance 1 meter. Make things simple. Assume Q1 is equal to 10 nanocoulomb, and this one is also 10 nanocoulomb. I want to know the force between them. Or let's say I want to know the force on Q2. In other words, what will happen here, Q1 is going to be, it will repel Q2, so it's going to push it away, you see what I'm saying? So the force is going to be on Q2, it's going to be in this direction. Make sense? I'm going to call that F1 because it is due to Q1, okay? And of course the force on Q1 is going to be F2 because it is due to Q2. So let's calculate, you know what, let me calculate the force on Q1 because for a good reason, I'll tell you in a minute why. So let's assume, find the force, find F on Q1, okay? As you can see, it is going to the left here, which makes it negative, okay? That's why I wanted to use that. So anyway, how do we do it? Simple. Use Coulomb's law. So I have the force is equal to K, Q1, Q2 over R squared. So that's 9 times 10 to the 9. Q1 is 10 nano, so that makes it 10 times 10 to the negative 9. And Q2 is also 10 nano, so that 10 times 10 to the 9 divided by the distance between them is 1 squared. See what I'm saying? Now, before I use the calculator, you can be smart about it. Just if you look at it, 10 to the 9, 10 to the negative 9 cancel out. I could probably get the whole thing without using a calculator. So that's going to be 10 times 10 here. If I don't, here, 10 times 10 is 10 to the 2 times 10 to the 9, that's 10 to the 11 times 9. So the final answer is going to be 9 times 10 to the, oops, not that minus, 10 to the 11. Is that right? There we go. Over 1 is just 1. So that's going to be what it is. So there we go. We have the unit. I want to make sure. I'm sorry. I think this is minus here, right? I apologize. The answer doesn't make sense when I looked at it. It doesn't make sense that the force is 10 to 11. So I made a typo here. This should have been a minus there, right? Because it's a nano. Let me do it all over. Sorry. So that's going to be what? So 10 times, let's say that's 9 times 10 to the 2 times 10 to the negative 9 rather, and that's going to be 9 times 10 to the negative 7 Newton. And there we go, that's the force of repulsion. One more detail on this, because the force here is in the negative x direction, so we have to put a minus sign, so I'm going to put a minus sign. I should have put it maybe here, so we have a minus sign there, and there we go, we have a minus sign here, indicating that it is to the left. See what I'm saying? And there we go, that's the force. Simple problem. Okay? All right, let's do something a little bit harder. Again, I'm going to go to the book. I'm going to start with problem number 22.3. Let me show it to you in the book. Make it a habit when you're watching the video, open the e-text on the side of your screen so you can look up whatever problem. I mean, just my opinion of that. So if I go to the, oops, I am already there, and it is on page 614. I thought that is a 614. 614. Okay, the example I want to do is 22.3. I'm sorry I had to stop the video to scroll the pages all the way to here. Anyway, so let me read the problem and then we'll work it out together. It says a small plastic sphere charged to negative nanocoulomb is held 1 centimeter above a small glass bead at rest on a table. Here it is. Here's the picture right there. This is the table right here, guys, and this is the plastic ball right here. The charge on it is negative nanocoulomb, and it is above the bead, or glass rather, ball 1 centimeter above it, as you can see here, and it's held somehow there and hovering in space, if you will. The bead is here, and then what's he said the bead has a mass of 15 grams. So the mass of the bead, I'm talking about the glass bead here, is 15 milligram rather, and the charge is positive 10 nanocoulomb. The question is, will the glass bead leap up to the plastic sphere? So we are assuming the plastic sphere, I guess it is fixed there. It's not allowed to move. And so there will be, so they both have the same charge. The distance between them is 1 centimeter. So if you let go of the glass bead, would it leap up and go up to the plastic bead, or it will just stay there? The question is, why would it stay there? Well, it has a weight, correct? I mean, there is gravitational pull on it versus a Coulombic attraction. You know, Coulomb's law, F, we're going to refer to it as Coulombic force. So what we want to do is to calculate the Coulombic attraction and the weight of the bead and see which one is greater. If the weight is greater, it's not going to leap up. If the Coulombic attraction is greater than the weight, then it will leap up to the plastic. Of course, we're assuming the whole environment is in vacuum. Okay, so let's do this problem. Let me take the book away, and I'll just use my OneNote here for the example. So here I have. So here is the bead, and that is the table right here. Here's the other one, the glass bead here. This is glass, and that's the plastic one. They are separated by a distance of 1 centimeter. Always draw a free body diagram, your own. And of course, this is Q1 is equal to negative 10 nanocoulomb, and Q2 here is equal to positive 10 nanocoulomb. And now we ask the question, what are the forces on the glass bead? Well, there are two. There is basically the weight, which is mg, right? The weight is mg. And then you get the Coulombic attraction, which is F. We'll call it F here. And there we go. Okay? So what I'm going to do now is calculate mg and F and see which one is greater. You see what I'm saying? So I can just say that if the Coulombic attraction, let me call it F sub c for Coulomb, F sub c is greater than mg, then the bead will leap up, right? Okay? So let me calculate mg first. So mg is just mass times acceleration due to gravity. He says that the mass is, I don't know, forgot, 15? Is that what it said? 15 milligram right there, right? Okay. So it is 15 milligrams, so that's 15 times 10 to the negative 3. That's milligram, and times gram. I want to make it into kilogram, so that's going to be times 10 to the negative 3 again, right? Kilogram. Times 9.8, and when I calculate that, I get 1.5 times 10 to the negative 4 Newton. Got it? All right. Now, the Coulombic attraction, F sub c, that's going to be k q1 q2 over r squared. So that's going to be 9 times 10 to the 9 multiplied by the product of the two charges. Q1 is, what is the Q1? Okay, here's one note, very, very important. Look at this charge. The charge here is negative, correct? And this one is positive. When you plug it into a vector formula, like a force or electric field, never ever put the minus sign. Never. Okay? It will mess up the direction. So never see if I put it, look at the diagram. The direction of it is what? Is upward. See, if I put a minus sign for that, that's going to be downward. So the minus sign will always mess up the direction of the vector. You see what I'm saying? So never ever put it. As a matter of fact, I think your book, when if you look at your book here, let me put it on the side here, on equation. Well, if I show you the solution of this problem in the book. And I just show you what he's plugging. Look at that. There is absolute value there. Why? To remind you that do not put the negative sign. Okay, so this is something that you want to keep in mind. As long as the quantity that you're using is a vector formula. Later on, we're going to study potentials and potential energy, and there is a Q. You can put that minus sign in there. It becomes attractive potential or repulsive potential. But for vector formula like force and electric field, you don't put that minus sign. Okay. Just a quick note. Anyway, so we have here 10 nano, which is 10 times 10 to the negative 9, multiplied by 10 nano again for Q2, 10 times 10 to the negative 9. All of that divided by 1 centimeter, which is 10 to the negative 2 quantity squared. Is that right, guys? And then we calculate that. And when we calculate it, I'm going to get 9 times 10 to the negative 3 Newton. There we go. Okay, so look at this force right here, the Coulombic attraction, and look at the weight. That's the weight, right? Which one is greater? As you can see here, if the Coulombic attraction is greater than mg, and therefore it will leap up. Okay? Easy enough? All right. Another problem. Problem 22.5. This one requires some trigonometry, vectors, lots of vectors. 22.5. There it is right here. Let me read it for you. There's the diagram right there. I'm going to draw a better diagram when we do it. Okay, it says 3 charged particle Q1, Q2, and Q3. Here they are right there. Should I make it bigger? Let me make it a little bit bigger. If I can find the darn thing. There it is. Okay, so it says 3 particles. Here it is. Q1, Q3, and Q2 right there. Q1 is negative 50 nanocoulomb, Q2 is positive 50 nanocoulomb, and Q3 is positive 30 nanocoulomb, are placed on the corners of a 5 by 10 centimeter rectangle. There it is right there. What's the net force on charge Q3? Right there, this one. Okay, due to the other 2 charges. Give your answer both in component form and a magnitude and direction form. Okay. This one is a little bit meaty, so you'll pay attention. Let me go to the notes. All right, first thing we need to do is to graph it. Always do a free body diagram. Believe me, it helps you see it better. Even if you see the free body diagram right in front of you in the book, actually you will do better by doing it yourself. Anyway, so example 22.5. And so we have this rectangle. It looks something like that. I'm still getting used to this stylus pen. Kind of hard to draw a straight line on it. There we go. And we have a positive charge here, a negative charge here at the corner, and a positive charge right here. This is Q2, which is equal to 50 nanocoulomb, Q1, which is equal to negative 50 nanocoulomb, and then we have here Q3. I'm reaching the top. Let me bring it down. There we go. Q3, that's equal to positive 30 nanocoulomb. And of course, I am interested in the distance between Q3 and Q2 right there. That's the distance. And then, of course, we have 10 centimeters here and then 5 centimeters here. And of course, we can find the distance between Q3 and Q2 in a minute. Okay. So how do we do it? Well, we want to put the vectors. You want to solve it because this is a two-dimensional problem, so you're going to have vectors here. So the question is, I want to find the net force on Q3, right? Q3 is right here. Okay. So first thing I need to do, I want to place all the vectors on it. Let me eliminate this for now temporarily because I need to have some space. And I'll bring it down a little bit, and I'll maybe change the color of the pen to red. You like red? Okay. So now this is Q3 here. So between this is Q3 right here. So between Q3, remember Q3 is positive, and Q1, okay, and Q1, there is attraction. So the force between them is going to look something like that. And I'm going to call it F1 because this is due to F1, to Q1. Instead of saying this is Q3 here. And then between Q3 and Q2, well, that's repulsion. So that's going to be along the dotted line, and it's going to be, I'll try my best to draw that thing. It's going to be something like that, okay? So that's going to be F2, okay? And, of course, the resultant is going to be something like that. Here is the resultant right here. Maybe I'll do a different color. Let me put it green. Is green cool? Green. So that is the resultant vector, okay? Your book, I think, calls it, let's do a better one. Okay, your book calls it F3, I think. Yeah, I'm going to call it R, like a resultant vector, okay? And so that's basically what we are interested in, finding this F net, which is R. Got it so far? Okay. So what I need to do is to resolve I have two vectors here. I have F1 and F2. Okay? This is very similar to what you studied back in the mechanics course. So basically you want to resolve the vectors. And to do that, so basically what I want to do, I want to resolve vector F2 and an F1 into X and Y components. And then from there, I can find the resultant vector. Okay? So to do that, let me go back to red. Oops. To do that, so here I have an angle. If I put horizontal line here like that, this angle right here, I'm going to call it theta. I'm going to need that theta because I need to resolve the components of F2, okay? And this angle, I hope you agree with me, it is equal to this angle, right? And this angle I can find easy, this theta, because I have the tris triangle and I know 5 and 10, so I can find it. So let me find that angle very quickly, once and for all. So basically what I have is something like that. And this is the angle theta, this is 5 and this is 10. So I can say that theta is equal to tan inverse of 10 over 5. And that will give me, if you do it, 63.4 degrees. Okay, so we'll keep that in mind when we start plugging data for now. Okay, that's the first thing. Now, let me find the force. Well, in this case, so let me find the force F1. Let me go back to black. I'm done drawing, maybe. So what is the value of the force F1? F1 is what? It's the force between between Q3 and Q1. Okay? And that's just the Coulombic attraction. That's going to be K Q1, Q3 over the distance between them, which is 10 centimeters, which is 10 times 10 to the negative 2 quantity squared. Is that okay? And when we do that, I will end up with, I'm looking at my notes here, I'm doing it a little bit different notation. But anyway, 1.35 times 10 to the negative 3 Newton. Okay? All right. Now, let me find the force. I'm going to dissolve the vector in a second, but let me find F2. Well, F2 is basically what? It's going to be Coulomb's law, KQ3 times Q2 over the distance between them. Of course, I can use the Pythagorean to find the distance, and it turned out to be 11.2 here. So that's 11.2 centimeters. Is that okay? So to do that, I have F2, excuse me, is equal to KQ2 Q3 over the distance between them, which is 11.2 times 10 to the negative 2 quantity squared. And then we calculate that, and when I calculate it, I'm going to end up with 1.08 times 10 to the negative 3 Newton. And by the way, while I was doing that, I noticed F1, as you can see, F1 here is a negative, so it's pointing downward, right? I intentionally didn't want to put the minus sign here yet, because if I'm going to put the sign, well, what is the sign of F2? You see what I'm saying? So I'll worry about, this is just a magnitude, okay? These are just magnitudes without worrying about direction yet, okay? So I realize this should be negative, but we will do that in a minute. Okay, now, what is the value, the vector R here? Well, the resultant vector is basically, in terms of vector form, is basically F1 vector. It's a combination of both of them, plus F2. Is that right? As a vector. All I need to do now is I want to find R sub x and R sub y, the component of that. Well, R sub x is what? It's going to be all the constituent x component of the vectors, which basically F1 here is along the y-axis, but the one that is x-axis is the F2 cosine theta. So Rx is going to be minus F2 cosine theta. Is that okay? I hope you're following me on that. So the R sub x is going to be this way, and that's going to be F2 cosine theta. R sub y, however, is two vectors. It's going to be F2 sine theta. It's going to be up here, right? Minus F1. Make sense? So that's going to be plus F2 sine theta minus F1. You see why the minus comes in? I mean, I didn't put the minus here, but it's right here. See what I'm saying? Okay, so there we go. So basically the problem boils down to those two. Finding those, I'm pretty much done with the problem. So let me find R sub x. So R sub x is going to be minus F2, which I found already. It's right here. Minus F2. That's going to be minus 1.08 times 10 to the negative 3. Cosine, the angle, I found it to be 63.4. It's right there, guys. Right here. And when I calculate that, I don't know if I calculated it already or not. I'm going to use my calculator. Go ahead and use your calculator. I hope you have your notes with you. And so in this case, I'm going to have 1.08 negative 3 times cosine 63.4. Answer, I get negative 4.83 times 10 to the negative 4 Newton. Okay? There we go. Now R sub y, that's going to be positive F2, which is F2 is the same number, 1.08 times 10 to the negative 3 times sine 63.4 minus, right? I'm following it from here, guys, right there. Minus F1. Well, F1, I found it to be there, so that's going to be minus 1.35 times 10 to the negative 3. I'm going to calculate all of that, and if you do the calculation, you will get negative 3.84 times 10 to the negative 4 Newton. There we go, r sub y, okay? So I got r sub x is right here, and I got r sub y right there, okay? I'm almost done with the problem. Now, he says in the problem, write it in vector form. Well, what is a vector form? The vector form looks something like that. A vector form is something like this. I have a vector, pick any arbitrary vector, A. That's going to be I A sub x plus J A sub y plus K A sub z. Is that what I'm saying? That's a vector form. This is how you draw a vector, IJK, okay? A component form is what you're looking at. Basically, a component form, would just say something like A equals to some number. I don't put a vector on top of it because that's a magnitude, okay? With respect, at angle, say, 30 degrees WRT with respect to the x-axis, okay? That would be one way to write it in terms of component form or magnitude form, okay? So I mean, they're both equivalent, okay? Of course, the upper one, this one is more elegant, but there is another way to do it. It's this way, okay? Equal to some number, you know, say 5 Newton at 30 degrees with respect to the x-axis. You see what I'm saying? So he's asking for both of them. So since we're done with that, so what is our r vector is equal to, which is this one right here, the green vector that I have drawn here. What is it equal to? Well, it's equal to, as you can see, it's a negative in the x-axis. See what I'm saying? And it is also negative in the y-axis. So that's going to be minus, one way to write it down, so Rx is going to be, let me write it this way, I R sub x plus J R sub y. Okay, it's a two-dimensional problem. So in this case, our vector is going to be negative, let me go like this, I, parentheses, 4.83 minus J, 3.84, bracket, times 10 to the negative 4 Newton. You see what I'm saying? That'll be one way to write it. Now, one more thing. What about the direction of it? What's the direction of this vector? In other words, here is the vector. Go back to the picture. I'm looking at this direction right here. So this is the vector. I'm talking about the direction of it with respect to the x-axis. So I'm looking at this angle right here, maybe. Phi, let's call it phi. So what is that equal to? Okay? That's the direction of the vector. I mean, it's sufficient to write it this way and be done with it. There it is, I'm done. That's the vector form. It's sufficient to write it this way, and that's it, you're done with the problem. But what if I am interested in also exactly the angle with respect to the x-axis? How do I do that? So phi is equal to, as you know, tan inverse of ry over rx. I'm sure you've done all of that back in physics 1. So that will be tan inverse of ry. I got the ry, which is right here. And rx, of course, is right there. And I'm going to put them as ratios to each other. The minuses will cancel out. 10 to the negative 4, excuse me, will cancel out. I'm left with 3.84 divided by 4.83 right there. And then, therefore, phi is equal to 38.5 degrees. There we go. Okay? So, to write it in a component form, if you will, it's going to look something like that. R, as a vector, let's say, is equal to, oh, sorry, I forgot to bring in the magnitude of this. Let me do the magnitude. So the magnitude, how do we do the magnitude? We do the Pythagorean. R is equal to square root of r sub x squared plus r sub y squared. And then we plug him in there. And then when you work it out, I think I did it already, so it's right here. And that's equal to 6.2 times 10 to the negative 4 Newton. Okay, so that's the magnitude. Don't put a vector on top of it. That's just the magnitude. So now the final answer, I mean, this is one final answer is right there. right here, this vector r. The other one, the other version of it, is that r as a vector is equal to 6.2 times 10 to the negative 4 Newton below, how about that, below the x-axis, by 38.5 degrees. There we go. That will be the vector as a whole. Okay? Got it? Okay. Okay, one more. You know what? I have one more to do, but this is, I think, is a homework problem. I would like to do it. But let me cover the electric field now. So we will, in this case, we would have covered the entire chapter. It's a little bit short, the chapter. It's not very long. So let me talk about the electric field. And then we'll do maybe a couple of more from the end of the chapter. So first of all, what is the electric field? The symbol of it is E, and it's a vector. Well, before I talk about it, if you remember the gravitational field, let's say, for example, I have an object in my hand, okay, and I'm holding it, and I release my hand off of it, if you will. You know, let's say I'm holding it between my finger, and I release my fingers off of it. What's going to happen? Of course, the object is going to fall to the ground, to the floor. And you ask the question, what caused it to fall to the ground? How come it didn't go up or to the side? Why did it fall? We say gravity. Okay. A more precise answer is this: is that the Earth has, as a mass, anything that is massive. Massive means it has mass. It doesn't make it big mass, but it's just something that has mass. So anything that has mass, there is an associated gravitational field towards it. Got it? And this gravitational field is always pointing downward toward the center of that object. So here is the Earth. One way to think about it, here is the center of the Earth. And what's happening, because the Earth has a mass, regardless how big or how small it is, if something has a mass, it gravitates. Even that cup of coffee in front of me, it gravitates. You gravitate. Anything gravitates. So there is an associated electric field. Let me draw them first. Electric field, gravitational field, I want to say. Gravitational field that is pointing downward toward the center of that object, say the Earth. Okay, this way. So this, and it's always in the radial direction. See that? It's always along the radius of the sphere, or whatever it is, the radial direction. In other words, it's not going like that. Let's say it's not going like this down. That's not radial. See what I'm saying? And so in this gravitational field, if I have an object here, if there is an object in the vicinity of that object, of this gravitating mass, what's going to happen to it? It's going to move with the gravitational field. The gravitational field pointing downward, so it's going to move with that gravitational field. So one way to see that why objects fall to the ground is because they're basically following the field. Okay, the field causes them or directs them to go toward the center of the Earth, and then they fall. Well, there is the floor, you know, forbidding them from going to the center, so they hit the floor and sit there. You see what I'm saying? And that gravitational field, we refer to it as G, the gravitational field. Well, similarly, we have something like this for in electricity, and later on we're going to talk about magnetism and magnetic field. However, this electric field comes in two flavors. One is emanating outward, away from the charged body, and one towards it. Okay, and that depends on the charge. See, and for gravitational field, we have a mass, and we don't have a negative mass or and positive mass or north mass and south mass. We just have mass, and that's why the field is only one kind, and it happens to be the attractive kind. It happens to be the one that is always pointing toward the center. Okay. For electric field, however, or magnetic field, well, they vary because depending on the polarity or the charge sign itself. Okay. So for a positive charge, let's say this one, you will have an electric field similar in nature, not in nature, I mean similar in similar to the analogous, let's say, analogous to the gravitational field, and it's always pointing outward. Always keep that in mind. Always remember that. Positive is outward like that, and that's the charge Q, and this is this field E, and it's a vector. And if it's a minus sign, if it's a negatively charged rather, so we will have that it's going downward into the charge, okay, like that. Both equivalent. This electric field and this electric field are equivalent, except in their direction, okay, where the charge, of course, here is negative, and this one is positive, okay. All right. Now here is the thing. If I want to talk about I want to find a way to describe this electric field in a more precise way. And when I say precise way, what does that mean? It means mathematically, okay? There is nothing more precise than mathematics. So I want to try to describe it in a more precise way. Here is how it goes. Imagine I have a charge, positive charge, okay? Which is similar to the charge that I have just drawn here. But for this, okay, so this charge, it has an electric field coming out of it like that, right? I'm going to call this charge Q prime, okay? I'm going to call it Q prime. Now, and we have an electric field on it. If I take another charge and put it in the vicinity of this charge, just like I have here for the gravitational field, I have, here is the Earth. Here is the Earth right here. Excuse me. And I have a mass that is sitting in the vicinity of it right there. I'm going to do the same thing. This is the big mass of the Earth or Moon, whatever. And this is a test mass right here, a little mass. So I'm going to do the same thing. So I have this charge, Q prime. And what I'm going to do, I'm going to take a test charge somewhere, let's say here, right there. And let's assume it is positive as well. Okay? And of course, remember, like charges repel. So it is now in the vicinity of the electric field of Q prime. I'm going to call it Q. Okay? So what's going to happen to it? What's going to happen is that the field will exert a force on it, as we all know, Coulombic force. A force on charge Q. This field comes from the charge Q prime, okay? And this electric field that is coming from the electric charge Q prime is equal to K Q prime over R squared. This is a very important equation. Okay? What's this R in this case? Well, R is the distance between the source charge, this one, the one that is producing the field, and the test charge, this Q. Okay, the distance here is equal to that. This force, F, which is in the radial direction, well, what is it equal to? It's equal to this force, this Coulombic force. Well, we know what the Coulombic force is equal to. I mean, it's equal to that, Q prime over the distance between them squared. But here's another way of writing it. This force is equal to the product of this electric field times the test charge, the charge of that test charge, Q. Okay? So now look at this. If I use this formula, this is a very, very useful formula. You're going to come to appreciate it in a minute. Okay, or QE, I like to write it QE rather than EQ. Okay, if I would plug in the value of E in it, that's going to be Q and then K, Q prime over R squared. Remember, I'm getting it from here. And of course, what you will see is that you come back to the Coulombic law. Got it? You got that? Okay. Let me give you a simple example, but again, memorize this formula. This is extremely important formula, and this one too. Okay, so far we have dealt with three formulas: Coulomb's law, the electric field, and the relationship between the electric field and Coulomb's law, QE. Okay, very important formula. So maybe you want to write them down and memorize them if you are not familiar with them, never seen it before. Let me give you a simple example. Let me go back to this again, just one more thing. So we said that F is equal to QE, correct? So that means E is equal to what? Is F over Q. So if I ask the question, what is the unit of E? Well, the unit of it is what? Newton per Coulomb. Okay, that's one unit. Later on, when we cover electricity, it turned out that electric field also volt per meter. Okay, which we'll do that later. We'll deal with that later. But for now, it is the unit of it is Newton per Coulomb, as you can see, Newton per Coulomb. All right, here's a simple example before we do a tougher one. Let's say I have a charge. Let's make it positive. Let's say 10 nanocoulomb, whatever, okay? And I'm interested in knowing what is the electric field here at this point. Okay, what's the electric field at this point? At the distance of, let's say, r equals 1 meter away. First thing, you want to ask the question, what is the direction of the field? Is it this way? Is it this way? I mean, both of them are away from the charge, because that's positive, and we said that the electric field is away from the charge. The field is always away from the charge. Well, both of them are away. This one is away, away, away. They are all away from the charge. But are they all electric fields? No. Always only in the radial direction. You get that? So all of that is not true. Only in the radial direction. What is the radial direction? Well, it's the direction of the dotted line. So you only have that electric field going that way, in the direction of this dotted line. Remember, it's a radial. It's always radial. Keep that in mind. Very, very important. So, and this, so you have here the electric field here. I can calculate it by using this formula. What is it? Right there? Nope. Right here. This formula right there. Okay? So the electric field is equal to KQ over R squared. Don't forget it's a squared. I hope I did it squared. Yeah. And then we just calculate it. So it's going to be 9 times 10 to the 9. Q is equal to 10 to the negative 10 times 10 to the negative 9 divided by R squared, which is 1 squared. And that will give me what? 9 and negative 9 cancel out. And this basically becomes 90 Newton per Coulomb. Here's the electric field. Okay. Now notice that the further I go from the charge, so this is at 1 meter, the electric field is 90 Newton per Coulomb. Now if I go even further somewhere, say here, for example, it's going to be further. What's going to happen to the field? It's going to be weaker. Why? Because it's also an inverse square law. Notice, notice that it is also an inverse square law. There is the formula right there. And as you can see, E is proportional to 1 over R squared. So the further you go, the weaker the field. You got it? So it is an inverse square law. And the closer you get to the charge, the more intense it is, and so on. Okay? All right, good. Let me give you an example that's a little bit more advanced, and that's from the book. An example from the book. It requires some trigonometry as well, and that's example 22.7. I hope it's not going to take me forever to find it. It's kind of hard to flip pages between in this. Oop, I'm in the wrong place. Sorry. It's on page 22.7. That's page 620. There is a trick to it, and that is you have to find out what is the section to go there. Otherwise, what page is that? It doesn't even tell you what page. It's crazy. Anyway, 620. I'm going to go electric field. and then page 620. There's no page number. Isn't that weird? Should be here, right there. You know, I'm gonna stop the video and I'll come back to you in a second. Sorry. Okay, I'm back. Took me like 3 minutes to find the page. There we go. Example 22.7, calculating the electric field. The diagram is right here. Let me just read the statement. It says a negative 1 nanocoulomb charged particle is located at the origin, and we have points 1, 2, and 3 have the coordinates, these coordinates respectively. Determine the electric field E at these points, then show the vectors on an electric field. Okay, I have the diagram in front of me, so I'm going to draw it, and it is right here. You can pause the video if you want to, or you can just use your own ebook and then look at it. Just keep it there on the side of your screen, but it's right here, figure 22.28. Okay, so I'm gonna draw it for you right here. It looks something like that. Again, I'm using my book right there, my hard copy. Here is the Cartesian system. Sorry, it's not vertical. And we have the rectangle, looks something like that. And then we have, this is point number 3. This is point number 2. And this is point number 1. And we have one charge, excuse me, we have one charge here, negative charge right at the origin, and it says Q equals to negative 1 nanocoulomb, and he's asking for what is the electric field at points 1, 2, and 3. So basically he wants find E1, find E2, and find E3, okay? Remember, these points in space, okay? So you're always finding electric field at a point in space rather than versus, say, the Coulombic force, where you're finding a force between two charges, okay? So as you can see here, I hope some of you are seeing it, is that points 1 and 2 are kind of easy to do. The harder one is number 3 because you have an angle. But anyway, we'll do the whole problem. So anyway, let me just put a line like that just to give me a sense of the distance. Now, if I come to E1, which is at point 1, what's the direction of that field? It's going to be towards, because it's negative, right? So that's going to be E1 like that. E2 similarly, it's going to be down towards it like that. And then of course E3 is also going to be like that as well. All towards there because it's a negative charge, right? If it's a positive charge, it's going to be away from it, okay? Then it also gives me the dimensions of it. What are the dimensions? Oh yeah, he gives me the point, the location of them. So the dimension here is, I hope it's 3. 1 by 3. 1, they're all 1, okay? So this is 1 and this is 1 as well, okay? That means what's the distance here is going to be square root of 2, correct? Which is 1.41, okay? And there we go. So let's work it out. So we're done with the creating the free body diagram and all the things around it. Now let's attack this problem. I know that the electric field, just to keep in mind, is equal to KQ over R squared. And I'm going to get E1. E1 is just going to be equal to, well, you agree with me it's equal to E2? But let's just we'll do that later. So E1 is going to be KQ over R1 squared, okay? So R1 is basically the distance from Q to point 1. I'm going to call it R1, okay? So when I do that, I will get with 9 times 10 to the 9 times, again, you don't put the minus sign. Remember, it is negative 1 nanocoulomb. E is a vector, so you don't put the minus sign, okay? Otherwise, it's going to mess it up. We put that minus sign, it's going to be a different direction. So it's going to be here as a magnitude, okay? We're not doing directions yet. So that's going to be 1 nano, so that makes it 10 to the negative 9 divided by r squared, which is 10 to the negative 2 quantity squared. Do you agree with that? Is that okay? And when we do that, this 10 to the 9, negative 9 cancel out. And when I work it out, I end up with 90,000 Newton per Coulomb. That's E1. Now, I hope you agree with me that E2, again, I intentionally didn't put the minus signs there for now. E2 is equal to E1 just by symmetry. Everything looks the same. That's just going to be 90,000 Newton per Coulomb. Okay? That's as magnitude. Remember, these are magnitude, not vector, so that's magnitude. If you want to do the vector, you put the minus sign. Okay. Now, let's do E3. E3 is a little bit tougher because it requires a two-dimensional, so it requires that you have to get components, because it's a vector. So you have to get components. And to do that, let me just get E3 by itself as a magnitude without components. Well, E3 is just going to be KQ over R sub 3 squared. And R sub 3 is really just the square root of 2. You see what I'm saying? And the square root of 2 is 1.41 centimeter, that is. So that's 1.41 times 10 to the negative 2 meters. And that'll be equal to 0.0141 meter. Is that okay? So that's the number I'm going to be using. So to do that, so I have 9 times 10 to the 9. Q is equal to 10 to the negative 9, 1 nano. So that's just 10 to the negative 9. Divided by the distance, 0.0141 quantity squared, like that. And when I calculate that, I get, I'm looking at it here in my notes, 45,000 excuse me, Newton per Coulomb. So E3 is 45,000 Newton per Coulomb. Okay. Now, I want to find the vector form of all E fields. Now I found the magnitude of all of them, E1, E2, and E3. It is E1 right here, E2 is right here, and E3 is right here. I did not bother with which direction, what sign. I didn't bother with any of that. I just found the magnitude. That's it. You know, it's like driving a car, okay, and you look at your speedometer and you're going 35 miles an hour. You're not asking, are you going north, south, east? Where are you going? You don't care. You just, the speedometer is just telling you, you're going 35 miles an hour, and that's it. Well, what if I want to know, well, which direction I'm going? I want to go north. Am I going north, south, east, northeast, whatever it is? Well, in this case, I need a compass or some kind of GPS to tell me, okay, you're going north. You see what I'm saying? So that's what we're doing here, is that I have gotten the speed, if you will, this is the speedometer. This is basically what my speedometer is telling me. But now I want to know the direction of those vectors. Okay, do you see what I'm saying? So now I want to find, so that would be the vector form. Is it along the x-axis, along the y-axis, or both? You know how that goes. So now E1 and E2, as you can see, it's probably easy to do. I can do it directly right now. So I can just say, well, E1, as you can see from the picture right there, I hope you're looking at it from your book, E1 is basically in the negative x direction. So that's negative I, right? So basically the form of that thing is going to be negative 90,000 I Newton per Coulomb. That's it. There it is. That's the vector in its full glory. That's the vector E1. Oops, with the vector form right here. Sorry. There we go. Okay. E2. Well, what is it? It's the same number, negative 90,000. Why did I put 90? Negative. It's because it's downward, right? 90,000 J in the y direction, Newton per Coulomb. There we go. No problem. Okay, everybody see that? Now I want to find E sub 3 as a vector. Okay. Well, E sub 3, as you can see here, it is kind of in between, it's two-dimensional, so I need to find the angle here. I have to get components. Let me put some, put a different color so you can see that. You like pink? Pink is cool. There we go. So I have here, this is E sub 3y, and this is E, I think I reached the top of the screen. Let me go down a little bit. It is E sub 3x. I need to find those. And by symmetry, because this this distance, this length is 1, and this length as well is 1. So basically the angle here, I can quickly find out it's 45. You agree with me? So that's 45. So basically it's going to look something like that if I'm going to write it down. And that's E3 as a vector. I can go like this. E sub 3. Now this is the x-axis. Cosine theta, the 45 degrees, I, plus E sub 3 sine, the 45 degrees, j. But I want to be careful with the angle. Look at the angles here. Actually, with the sign. Look at the vectors. This vector is in the negative x direction, and this one is the negative y direction, so I have to put out minus signs because it's just a direction. So that's going to be a minus here, and that's also going to be a minus here. See what I'm saying? There we go. The next step is I just put in my numbers. So it's going to be minus, E3 is what, guys? It's right here. That's going to be minus 45,000 times cosine 45, which is 0.707. Memorize it. It always pops up. Minus 45,000 times sine 45, same thing, j. And when I work it out, I will get negative 31800I minus 31800J as the electric field. There we go. Oops, I forgot the unit. Newton per Coulomb for both, right? Newton per Coulomb. There we go. Is that better? Okay. Okay, great. One more. There is one problem. There's a little toughie from the back of the book, and I think it's homework. I'm going to do it. Number 62. It's the last problem in the homework, I think. You pay attention to it. It's not terribly trivial. I'm sure a lot of you think it's not bad, but it's a little bit hard. Requires some work. And maybe if I have time, I want to do also either 67 or 68. They're very similar. So you need to know both, at least for the midterm exam or something. It's a nice problem. Those two problems, 67 and 68. I'll do one of them here, or at least I'll just give you a sketch on how to do it. And then I'm going to do 62, and that will call it a day for this video. All right. Go back to black color. Number 62. Okay. So, let me show it to you in the book. Maybe I have to, I'm going to have to, 23, there we go. I think this one. And I have to scroll. How do I do this? Oh, okay, I can just scroll down. Okay, I hope so. Okay, 62. There we go, this one right here. I don't know what INT stands for, but anyway, there it is. As you can see here, you have, it looks like a double pendulum or something, but that's the picture that we're looking at, okay? Let me read it and I'll explain it to you. It says 2 5-gram point charges. So I have two balls here, if you will, each of them 5 grams, both positively charged, okay? And they were, you know, imagine that they were not charged, okay? Let's just say 2 balls, each 5 grams, and they are hung from 2 strings, so they were kind of together, and then you charge them, and it will happen to them. They will separate because of the repulsion between them. Make sense? Okay. So he says a 5-gram point charges, 1 meter long threads repel each other after being charged to 100 nanocoulomb. Got it? Question: what's the angle theta? You can assume that theta is a small angle. Okay? That's the question. All right. The last sentence is an interesting sentence. You may say, why would he do that? Why would he say something like that? I'll tell you why in a second. But basically, so let's do this problem. So it looks something like that. Here is the pivot right here. I have one here and one there. Here's the ball 1 and ball 2 like that. Both positive. Okay. And one is 5 gram. Both of them actually is 5 gram. And then this one is 5 gram as well. And the charges on them is 100, I think. Is it 100? 100 nanocoulomb, and then this one 100 nanocoulomb. The numbers, we will worry about the numbers later. And each of them has a length let's call it L, 1 meter, both of them. And then there is an angle between them, and the theta is, each of them is a theta. So I'm going to draw a line that split them, a bisector, if you will. That's theta, and this is also theta, like that, okay? And the distance between them is not mentioned to us in the problem, is it? It's not given to us in the problem, okay? But there is a distance between them. I'm going to call it R for just the sake of simplicity. So we're just going to call it R, okay? So that means this would be from here to there. That would be R over 2, but that's for later, okay? So, and then he's asking, what is the angle theta? Okay, that's basically what he's asking for. So how do we do this problem? Okay. Here's how it works. Watch and learn. I take one of the balls. Let's say I'm going to take this ball right here, okay? And then I'm going to put all the forces on it, okay? So here is the part of the string. Here's the ball. And there is the angle theta right here. What are the forces on it? Well, there will be mg of the ball. How do I know that? Well, he gives me the mass. He said it's 5 grams, so there got to be a weight there, right? And then there is a tension in the ball. There is always a tension whenever you have a cord or a string right there. So there is a tension in the cord. T, we'll call it, okay? And what else? Well, the balls are being repelled by each other, so there is a coulombic repulsion between them. And what's the direction of that coulombic? Is always in the radial direction. So it's going to be this way. I'm going to call it F sub c. Okay? And there is really nothing else. These are, so I have 3 forces on it. The only problem here is that I want those forces to be in the X and Y direction. Okay? As you can see here, the tension is kind of a between X and Y, so I need to resolve it. But F sub c is fine, and the weight is fine. The weight is in the Y direction. The coulombic force F sub c is in the X direction. I just need to resolve the tension, okay? So how do I do that? Well, if this angle is theta right here, so that means the angle here is theta as well. So in this case, let me change the color. Oh, this one, I'll put the red there. So that's going to be, there'll be a force, a component of the tension, T cosine theta, instead of saying. And then there's another one here, is T sine theta. And I can just ignore the tension T here, this big T. I can use those Okay, and there we go. I have now all the forces resolved in x and y. This is the goal. You always have them resolved in x and y axis. All right, so let's begin the solution. So the sum of the forces in the x direction equals 0. Why is it equal 0? Well, it's not moving. It's in a static situation. It's not MA, right? So it's all in a static situation. So the force in the x direction is going to be F sub c minus t sine theta, and that's equal to 0. I'll come back to this F sub c in a second. Sum of the forces in the y direction is also equal to 0, and that's going to be t cosine theta minus mg equals 0. Got it? Remember, I'm interested really in finding theta. So, and I'm not interested in the tension T, so I'm going to eliminate it. To do that, I go on the second equation right here, and I solve for T. T in this case will be equal to mg over cosine theta, because I want to eliminate the tension. I'm not interested in it. And then I'll take that and plug it back in here. Got it? So when I do that, F sub c minus mg over cosine theta times sine theta equals 0. This basically tells me F sub c is equal to mg tangent theta. So far so good. I'm interested in what? Finding theta. So I'm going somewhere. Everything is fine so far. Now I need to know what is F sub c. Well, look at the diagram again. The original diagram right here. There is an F sub c like that. Allow me to lay that out. So that's going to be F sub c like this. And then there is F sub c like this. And so the force, that's a Coulombic repulsion. And the distance between them is r. Right? I need to find r. Is that what I'm saying? Okay. How do I do that? Well, first of all, F sub c is equal to what? K, Q, oops. Remember, each ball has a charge Q. 100. But we'll do don't put the numbers until you are done, completely done with analysis. Okay, so never put the numbers early. So each of them is Q, so it's just going to be Q squared over the distance between them squared. Okay? And as you can see here, this R right there, this R right here, this would be R over 2. So I have a triangle with an R over 2 on it. Let me draw that triangle. So it looks something like that. This is R over 2. Remember, I'm interested in the angle theta. And this is 1 right here. So as you can see here, what is opposite and hypotenuse? That's a sine. You agree with me on that? So I can say that sine theta is equal to R over 2 over 1. Opposite over hypotenuse. So sine theta is R over 2. So therefore, R is 2 times sine theta. Okay? Now I go back and plug it here. I'm going to plug everything. I'm going to plug in what? I'm going to plug in this one right here, guys. I'm going to plug in this into F sub c and the R for this one. Okay? So I'm going to do all of that. So let's see. So F sub c is going to be K Q squared over R squared equals mg tan theta. But R is equal to what? Is equal to 2 sine theta. I'm going to plug it right there. So that's going to be K Q squared over 4 sine squared theta equals mg tan theta. Remember, I'm interested in what? I keep repeating myself. Theta. Good. So let's solve for theta. So cross multiply, and I'm going to end up with sine squared theta times tan theta is equal to K Q squared over 4 mg. I end up with this equation. Is that a nice equation? Is that a nice equation? What do you think? No, it's not. It's actually, you can't do this problem. Look at that. Look at the trig problem, the trigonometric expression to the left. Sine squared theta times tan theta equals to a number on the right. Whatever that number is. You can just plug in the number, you'll get a number there. How in the world am I going to get that theta? Is there an algebraic way to do it? Maybe there is. But as you can see, it's very tedious. You agree with me on that? I wanted to appreciate the difficulty of this expression. This expression is not a simple expression. It's actually a monster. The left-hand side, I cannot think of an analytic way to get the value of theta. Let me elaborate. Let's calculate it, because I wanted to appreciate why I chose this problem. It's a very nice problem. Let me calculate all of that. Okay, so that's k is going to be 9 times 10 to the 9. Q squared, that is 100 times 10 to the negative 9 squared divided by 4 times the mass is 5 grams, 5 times 10 negative 3 times 9.8. And when I calculate all of that, did I do this problem? I don't have the solution to it. Okay, let's all of us get the calculator, work it out, and let's hope we get the same answer. So I'm going to calculate this whole thing. So it's going to be, bear with me. Divided by 4. Divided by 9.8. Divided by 3. I hope I didn't make any mistake. I got the following answer: 4.59 times 10 to the negative 4. Okay, I think it looks fine. I'm expecting a small one. Anyway, sine squared theta times tan theta. Let's assume this is the right answer. And there we go. I got this. Now, can you solve that? And the answer is probably, I mean, it will probably take me, I don't know. I've never really attempted to solve it. But maybe there is a way to do it. You can use a computer program like Mathematica or something like that, Maple or something, to give you an approximation. But here's the good news. Let me show you the good news. Go back to the problem. Remember I told you about, here is the problem. There is look at the last sentence. He's sneaky. He gave you this sentence. Why did he give it to you? He's not being nice when he gave you this one. He said, you can assume theta is a very small angle. Why? What does that mean? What's the wisdom of that? This is called the small angle approximation. Please remember it. This is very, very important. It's going to pop up in this course 3-4 times. But remember it forever. I mean, it's something that you will see many, many times in your future courses and your daily life as an engineer or a scientist or a physicist, whatever. Small angle approximation. For those of you who don't know what that means, when the angle is small, okay, when theta, I'm talking here the angle in radian, when theta is small, okay, what will happen is that sine theta is almost equal to theta, and cosine theta is almost equal to 1, okay? And that's a rule, remember that very, very, very well. Now, we know that tangent theta is equal to what? Sine over cosine, correct? Well, if the angle is small, that means tangent theta is almost equal to what? Is almost equal to theta over 1, and therefore, in other words, tangent theta, that's what I'm saying, is almost equal to sine theta, but sine theta is equal to what? Theta, and therefore, tan theta is almost equal to theta. That's what I'm sorry, I'm writing it again. But there we go. These are what is called the small angle approximation. Remember it. Write it down somewhere. They come in really handy. And what's going to save you in solving this problem is to use the small angle approximation. Why do I use the small angle approximation? Because he told me. He said you can assume theta is small. See, if you didn't say that, now you're stuck with an expression that you need to find out a way to solve it, a trigonometric expression. But he says that to save you, to help you. He knows that you're going to end up with this expression at the end when you work it out. So now, with this in mind, it becomes a trivial problem. Look, go back to it again. Here is my expression. Again, I'm reaching the edge of the screen. So I have here, and I'll write it down again, sine squared theta times tan theta equals 4.59 times 10 to the negative 4. So theta squared, sine squared theta and tan theta, well, these are all thetas. That's going to be theta cubed equal, is that nice like this? To negative 4. And then therefore, theta is equal to 4.59 times 10 to the negative 4 to the power of 1/3. We're going to calculate that, okay? Now, you be careful when you calculate. Let me show you what that means. 4.59 negative 4. And then you're going to take the square root, excuse me, the cube root of that. The power of 0.333. Answer, I'm going to get this. 0.077. 0.077 what? Radian. Okay? Radian. Now the answer, I believe, in the back of the book or in mastering is in degrees. So you want to convert radian to degrees. How do you do that? Well, you just 180 degrees divided by 3.14 radian. Is that right? And then you work it out, and I believe, I think it's 14 if I remember correctly. I've done this problem last year. 0.077 times 180 divided by 3.14, which is pi, right? And that's equal to 4.4, sorry, 4.41 degree. As you can see, it's a very tiny angle. And there we go, that's the answer. Got it? Okay, this is a very, very nice problem. Very nice. All right, the last problem that I want to do, and we will wrap up the chapter, is problem number, again, one of them, number 67 or 68. If we were in class, I would have told you which one do you want me to do. Let me do, the equivalent, similar. Let me do 67. And I don't think it's homework, okay? Both of them are not homework. So you have something similar, okay? So what you have in here, you have, here's a pivot, here's a string hanging from the ceiling like that. And there is the rope, a string of that is. And then you have at the end of it is a mass, a ball or something like that. And it is 5 grams of charge Q. And then you have an electric field coming this way, parallel. Okay, and he says, oh, sorry, I forgot that we have the problem here. Let me scroll down to it. Number 67. Number 67 right here, and here is a picture. This is 68. As you can see, they're very similar, where here Q is not given to you, but theta is given. Here, theta is not given, but Q is given. See what I'm saying? They're both equivalent, though. All right, let's read the problem. Here is the picture right there. He says, an electric field, 100,000 I, of course, in the direction of x-axis, Newton per Coulomb, causes a 5-gram point charge in the figure to hang at 20 degree angle. He's asking, what is the charge Q on the ball? Okay. So you have this electric field coming this way, and then what is the value of Q? Got it? Okay, let's do it. 100,000, I need to remember that. So E here is 100,000, that makes it 10 to the 5th I Newton per Coulomb. Okay, first of all, you may wonder, where is this electric field coming from? When you see an electric field like that. Before I do this problem, let me just show you something here. Imagine I have two metal sheets, okay? Two metal sheets. Maybe as big as 8.5 by 11, you know, a typical, you know, size of a, you know, printout sheet, whatever. Here's one metal sheet, and here's another one here. And I put them side by side, parallel to each other. And I connect, and I have here a battery. Looks like something like a car battery or something like that. Here's the positive terminal, here's the negative terminal. So I connect this positive terminal to this sheet and the negative terminal to this sheet, okay? And I turn the switch. There's a switch right here, and I close the switch. And so what's going to happen is that this sheet's going to be positively charged, and this is going to be negatively charged, right? Now, this we call a capacitor. We're going to cover the capacitor in details this semester, but that's later. So you have a capacitor. Let me draw them in 2 dimensions. This is like 3. So here is a capacitor. Here's the 2 plates that we're talking about. This is negative. This is positive. Okay. As a result of that, because this is positive and this is negative, you will have a uniform electric field between them like that. Remember, it goes from positive to negative? So you'll have an electric field going like that. Right? Now, if I put this apparatus right here, this apparatus, this diagram that you're looking at right there, if I would put it right in the middle between the sheets like that, that's exactly the picture that we're talking about. Here is the wall, here's the ball right here, and it is, what is it, positive ball? Oh, of course, if it's going to be going that way, well, here is the ball, and let's say when I put it, what's going to happen to it? It's going to move, let's say, in this direction, as you can see here, it's going to move in that direction. So what is the origin of this electric field? Well, most likely there is like a capacitor here in between. You see what I'm saying? And since it's moving this direction, and the electric field is this way, is in this direction, and it's always the electric field goes from positive to negative, correct? The positive is a source, the negative is a sink. So this must be positive, and this must be negative. Now, since the ball is attracted in this direction, the ball must be what? Positive or negative? Got to be positive. Because if it's negative, it's going to be attracted to the positive plate here. So now I know, he said find Q. Well, I know one thing about Q. It's got to be positive for sure. You see what I'm saying? You see those hints? Okay, good. Now let's go back to the problem. So what I have this apparatus, and I want to know what's the value of Q. The question is, what are the forces on it? I'm going to do it. It's similar to the problem that we've just done. Again, always when you solve a problem, solve it symbolically. Don't put the numbers too early, okay? You're no longer a high school kid. Always solve them symbolically. So you put the formulas, you work out the algebra, and then at the very last step, when you're done, you have the final expression, then you put in your data in there to get the final answer, okay? You always solve it symbolically first. So even though he gives you the angle of 20 degrees, right? Just keep it theta. Just keep everything symbolic, because for the reader who's reading your report or whatever you're doing, he or she will be able to understand it symbolically rather than just a bunch of numbers in there. Okay, so how do we do this problem? I'm going to erase those. I'll just leave them. It's okay. Let me just draw it again here very quickly. And it's going this way. Here's the electric field. And it's equal to 10 to the 5th Newton per Coulomb. And it's in the in the x direction like that. And now the question is, what are the forces on it? Well, he says it has a mass, so they got to be an mg here. And they got to be a tension T, just like our last problem. And of course, that's the Coulombic attraction towards the negative plate, correct? From that previous picture. There we go. And this is angle theta. Now, here is a question. What is the value, or what is the expression for the Coulombic attraction here? You think about it while I go to the next step. So what I want to do now, I want to resolve the vectors. So I'm going to go with the tension is going to be two components here. One component is t cosine theta, and then this one is t sine theta, correct? So now sum of the forces in the x direction equals 0, and sum of the forces in the y direction equals 0. The whole thing is in a static situation. It's not an oscillating pendulum or anything. So in this case, here I have f sub c minus t sine theta equals 0, and then for the y is t cosine theta minus mg equals 0. Again, I want to eliminate the tension t, just like I did in the last problem. So mg over cosine theta, I can put it back in there, right? So that's going to be f sub c equal t sine theta. I just move the t sine theta to the other side. And that's going to be mg tangent theta, just like we did in the previous problem. There we go. Here's my final expression. But there is one more thing. What is f sub c? Well, you can pause the video and think about it, but here it is. Well, we know that f sub c is k q1 q2 over r squared. That's what we learned, right? But is this expression applicable to our case? Think about it. There's no charge. There's no two charges. There is one charge right here. I mean, it's a q, which I don't know anything about. So let's assume it is q1. Well, what is q2? What is that q2? The answer, really, you cannot use this expression because we don't know the charge too. However, we can use, since he gives us the electric field right there, we can use that other third expression that we studied in this chapter, and that is the force is equal to QE. Isn't that cool? That's the one we're going to be using. Q here is the one that we are looking for, and the electric field is given to us. In other words, I go back to this formula, and I go, this is QE equals mg tangent theta. Theta is given to me. Mass is given to me. The electric is given to me. I'm done with the problem. So Q is equal to mg tan theta over E. So that will be simple. It's going to be, what is that, 5 grams? 5 grams. So that's 5 times 10 to the negative 3 times 9.8 times tangent 20. As you can see, I am plugging numbers only in the last step, divided by E, which is 10 to the 5th, and then we calculate that, and we will get the value of the charge. Let me calculate that. I don't have it in my notes, this problem. So it's going to be tangent 20 equals to times 9.8 times 5 negative 3 divided by 1,000. Answer, my final answer for that. The charge here is 1.78, if I did it correctly, times 10 to the negative 7 Coulomb. Okay? Or you can just say Q is 178 nanocoulomb. And there we go. Okay? I think I'm going to stop here. And please let me know if you have any questions by posting it under the Ask the Professor. And that's it. Have a good day.